Electric potential or voltage plays an extremely important role in university physics too. In UP1, you studied something like a potential, but you were more inclined to call it potential energy. For example, if I had a mass located some distance above the Earth's surface, then that mass relative to the Earth's surface, in other words, if you took the Earth's gravitational potential energy equal to zero on the surface, then relative to that, you would say that mass m has got a potential energy mgh. And if you think of the height as 1 meter, that's mg times 1. Okay, and if the height were 2 meters and you took the object to that new level, the potential energy would be mg times 2. In other words, it had a higher potential energy the further up you take it from the Earth's surface, assuming that the gravitational acceleration does not change very much. That's pretty true for being very close to the Earth's surface. So this concept was pretty familiar to you. You also know that if you keep an object at this point and let it go, its natural tendency will be to fall down, because nature always tries to reduce the potential energy and convert it to some other form of energy, in this case kinetic energy, because this mass will be moving pretty fast. And then if it comes down even more, it moves down even faster. Actually, if you think about it, that is the direction of the gravitational field also. So in a sense, you get this idea that as potential energy decreases, it tells you the direction in which the gravitational field also acts. It's in the direction of decreasing gravitational potential energy. So these insights from UP1 are extremely useful and will be carried over without any change to UP2. So the precise analogy of potential does not exist for the gravity example. But for the electricity example, the change in potential is given by the change in potential energy per unit charge. Now, if you think about the gravitational analogy, that would be the change in the gravitational potential, delta V gravitational, would be equal to delta U gravitational divided by mass. So it's as though this level has got a potential of G times 1, that level has got a potential of G times 2, and when you introduce a mass, then the potential energy can be found by simply multiplying the potential by the mass. Here, you would, to find the electrical potential energy, you would multiply the electrical potential difference by the charge. So the other equation that I would like you to compare this to is something that you already know, and that is the electric field magnitude is the force per unit charge. So you see, the electric field is force per unit charge, whereas the electric potential difference is the potential difference per unit charge. So there's a very close relationship between these two, and we will explore that. Now, to make that clear, let us also talk a little bit about conservative forces, which is a subject that you studied in UP1. A force is called conservative if it satisfies one of many conditions, and the most important condition is that the work done does not depend on the path taken. So if you have a particle that goes from some initial point to the final point F, it really should not matter how you move that particle. You could go in a very complicated fashion, but the work done only depends on the displacement between the initial and the final point, and not on the complications of the path taken. Okay, that's the meaning of conservative force. For example, gravity is a conservative force. You can come down from here to here either in a straight line, or you could go to China along this level and then come back down in China and then come back here, and the amount of work done by gravity will be the same, because it costs nothing to move it along a line of constant gravitational potential energy. That line, by the way, is called an equipotential. Gravitational equipotentials close to the Earth's surface are parallel to the Earth's surface, and electrical potentials are like that. Now, how do we summarize this concept. The work done is independent of the path taken. Well, the work done by a force is given by the integral of the force dotted with the displacement vector ds. So that's a general definition of the work done by any force in UP1. So the ds vector here is the infinitesimal displacement, and the force in question can be pointing in some arbitrary direction at some point, and the dot product refers to the angle between f and ds, and that angle keeps changing as you go from point to point along this complicated path. So that's the work done by a general force, any force, even the force of friction, for example. We would have to specify the path taken. So this is not a good way of writing the work done by a force unless you say what path is taken. So we'll say along the path gamma, gamma being this dotted path. That's the general definition of any force. Now, if the force is conservative, you would write I to f dot ds, and you'll put any path down here. That lets whoever is reading it know that, oh, they're talking about a conservative force, not just any force. So when you put wf equals any path, that's when you know that it's a conservative force. With that notational thing out of the way, I'm also going to remind you a little bit of what property a conservative force has got. A conservative force can also be written as the negative change in the potential energy. So there's an associated potential energy function, delta U, associated with that force F. Now that is a property, and that negative sign is pretty important. You can see why that negative sign is needed for the gravitational example. The work done by gravity in going from here to here is positive because the force of gravity is down and the displacement is also down. So the force dot displacement is going to be gravitational force times displacement in a down direction times cosine of 0 degrees. So that's going to be a positive work. But the change in the gravitational potential energy has been negative. You've gone from a higher gravitational potential energy, which is mg times 2, to a lower gravitational potential energy, or mg times 1. So you actually have gone down in potential energy. So for that reason, you need the minus sign to write the work in terms of potential energy. Now what I'm going to do is I'm going to now specialize to electric force. First of all, I'm making the hidden assumption here that electric force is conservative. In fact, it is. In more advanced classes, you can actually show that Gauss's law leads to the fact that the electric field is conservative as long as something else is satisfied. Okay? If, and this condition I'm about to state is quite mind-boggling, if there are no magnets moving around. Now, that's a very strange condition. Electric field is conservative if there's no magnets nearby that are moving. Okay? Now, one of the things that you'll learn later on in this course is that even if a charge moves, you've got a magnet. A moving charge is a magnet. So that's one of the crazy things you're going to learn soon in UP2. So this means that electric fields are conservative only if there's no moving charges nearby compared to where the electric field is. Okay, so that's a very strange result. Assuming that this is all satisfied, electric field is conservative, we can apply this scheme that you learned in UP1 to the electric force. So the work done by the electric force, which I'll write as WFE, must be equal to the negative change in the electric potential energy, which I'll simply write as delta UE. And that should also be equal to this type of definition with any path down there. So that's going to be equal to the integral from I to F of the electric force dotted with the displacement vector ds along any path. Now what I'm going to do is I'm going to divide both sides by q. If I divide the left hand side by q, I'm going to get negative the change in the potential. And on the right hand side, if I divide by q, the electric force divided by q is just the electric field. So I'm going to get integral I to F along any path of the electric field dotted with the displacement vector ds. Now the negative sign here does not look good, so I'm going to transfer it over there. So I get delta v equals negative the integral from I to f along any path E dot ds. This is an extremely important equation, and it tells us how, if you know the electric field in every point in the region that you're interested in, you can actually find a change in potential energy due to that. And once you have the change in potential energy, life gets really simple. All you've got to do is multiply it by whatever charge you have, and you can find the change in potential energy, and from that you can find out how quickly the charge is moving. Life becomes really smooth and interesting after that point. Now, I will consider this as my master equation, but there are a couple of approximations that you can make and make that a little bit down to earth. We'll soon, in future videos, learn how to work with that directly. But for now, I want to talk about a couple of approximations that we can look at. The first approximation is the electric field is constant everywhere, in both magnitude and in direction. If the electric field is constant in both magnitude and direction, this integral just becomes a solid value. So let me write E equals constant, and I'll put the vector sign on top of the constant too to let you know that it's constant in magnitude and in direction. Then delta V becomes negative E dot d, where d is simply that displacement vector going from the initial point to the final point directly. Now if you expand the dot product, that gives me ed times cosine theta, meaning that, let me draw another picture here to illustrate what's going on in this special case only. The electric field is the same everywhere, which means that you're just going to draw a bunch of arrows, okay? And you have a path. I've gone about it the opposite way. I've drawn the electric field first, so I can thread this path through it. And there's some initial point I, and there's some final point F. Now, if the electric field is constant, and it is in this case, all I need to do, this equation is telling me, all I need to do is to draw the displacement vector from the initial point to the final point. Displacement vector means you start the tail at the initial point and end at the final point. And then there's an angle theta, there's a global angle theta that exists between E and the displacement vector, and that angle theta will never change, okay, from point to point. Even though this is going on the crazy path, it doesn't matter, because the angle between the displacement vector and the electric field will always continue to remain theta, okay? So that's what this equation is telling us. Now, by the way, in applications, it's also useful to know how to do this in Cartesian coordinates, and that would be E sub x times d sub x plus E sub y times d sub y plus E sub z times d sub z. So you break it up into x, y, and z components. The second thing that I want to talk about is a slightly more general result than that. This just applies to many situations, and that is an approximation of what the parallel component of the electric field is. So what I'm going to do here is just take a little portion of that path. So suppose I have a small portion of that path, I'll call that delta S, and let's just say I'm going from I to F over a very small portion of that path. And let's suppose the electric field is Fe. Now for this one, I'm not assuming Fe to be constant or anything. It can change from point to point. But can I make any statement about this electric field? Well, for one thing, I can decompose it into two components. I can decompose it into the perpendicular component to the delta S and the parallel component along the direction of delta S. So let's write down an expression for the work done by the electric force. Work done by the electric force, which is equal to F sub E dot delta S in this case. Well, I can write F sub E as F sub E perpendicular plus F sub E parallel, because of the decomposition I've illustrated in red, dot delta S. Now delta S and F sub E perpendicular make a 90-degree angle, so the dot product simply vanishes. So I'm just left with Fe parallel times delta S times cosine 0, and so that's just Fe times delta S. Now WFE is also equal to negative Q times the change in voltage, because WFE, recall, is equal to negative delta UE, and delta UE can be written as Q times delta V. That's what I'm doing here. So negative Q times delta V is equal to F sub E, but F sub E is also Q times the electric field parallel delta S. I'll cancel the Q's on both sides, and here I have a beautiful understanding of what the parallel component of the electric field actually represents. It represents the rate of change of voltage with respect to the direction delta S. So this is a very useful equation to use for any situation.